All right, so we're going to start out by taking a look at section 4.3. We have 2 sections left in chapter 4, today and tomorrow. And then Wednesday will be our first section of chapter 5, which is the last chapter before we start trig. So chapter 6 will start trig, and that'll probably be probably next academic week, but you got the double shock week in there, so it's still going to be a little ways away, probably beginning in December. I think we'll start trig. All right, so we're going to look at how do we solve equations that contain rational expressions. So just a reminder about what a rational expression is. It's when you have a fraction and you have a polynomial in the top and in the bottom. Let me show you a quick example of one we'll do. Here's an equation with 3 rational expressions. 2x is a polynomial, x minus 1 is a polynomial. When you put them in a fraction, that's called a rational expression. And when you put a bunch of them and then put an equal sign between them, that's a rational equation. Right, so we'll look at how do we solve something like that. So the first one we're going to solve, we're actually going to figure it out ourselves. It's going to be from a word problem. And there's a formula that we're going to need to do this first word problem. And it's the distance. It relates distance, rate, and time. So if you don't remember that, you would have learned it at some point in Algebra 1. You might have even reviewed it in Algebra 2. But it's distance equals rate times time. So d is distance, r is your rate, or the speed, and t is the time. So we're going to look at an example where somebody's going to be taking a trip, and they're going to have 2 modes of transportation that they use. I think they're going to take their car for part of the trip, and then the second part they get on a train and they go from there. So that's kind of the background about this problem. So it says that Sue drove 30 miles to a train station and then completed her trip by train. She traveled a total of 120 miles, 30 of which were by car. Now, we don't know how fast the car went or how fast the train went, but they do tell us the average speed of the car, or the average speed of the train, is 20 miles per hour faster than the average speed of the car. So there are really 2 things that we don't know about the train and the car. And it's the same thing. We don't know about either one of them. Can anybody tell me what we don't know about the train and the car? We don't know the what of either one of them. Yeah?
Time.
Okay, we don't know the time, and we don't know what else about them. Sarah?
The speed.
We don't know the speed. Okay, so what we're going to have to do is pick a variable to represent the speed of one of them, and then we can represent the speed of the other one in terms of that variable. So we're going to let x be the speed of the car. And what they want us to do is find a formula that represents the total time to do the trip. Okay, so I'm going to have a formula that says like t of x equals, and then if you tell me how fast the car was going, I can plug in that, and it'll tell me the total time for the whole trip, train and car together. So the first thing we're going to do is we're just going to try to think of like the big picture idea, and then we'll kind of work down to getting an equation. So we want to figure out the time. Okay, and I'm going to call that the total time. Because how many modes of transportation is, what was her name, Sue, or whoever? Yeah. How many modes of transportation is Sue taking in this problem? Yeah? 2. What are they?
The train and the car.
The train and the car. So she's going to spend some time in the car, and she's going to spend some time on the train. What are we going to do to find the total time if we know the time she spends in each mode of transportation? Yep.
You're going to add it.
We're going to add them together. So the total time is going to equal time in the car plus time on the train. Okay, so that's kind of that's the big picture idea of what we're trying to figure out. And they told us to use capital T, and we're going to write time as a function of x, where x represents the speed of the car. Now, let's think about time a little bit. Okay. The formula I had up above was distance equals rate times time. How would you solve that formula for t? So instead of having it solved for d, I want to get t by itself. Casey? Yes, I would like to have something that looks like that.
Divide by r.
Yep, you divide each side by r. Very good. So distance divided by rate equals time. Right. So let's kind of make that substitution in here. So instead of writing time in car, I'm going to write it like this. Distance in the car divided by speed of car. Because distance divided by rate gives me time. So this is the same thing as saying the time in the car. Plus the distance on the train divided by the speed on the train. Or speed, I'll say speed of train, that probably makes more sense. Distance divided by speed will give me time again. Questions on that? Now I have 4 things to fill out. We're going to scroll up in the word problem and see if we can figure them out. The distance she travels in the car. What's the distance that she traveled in the car? 30
miles.
30 miles. Divided by, what's the speed of the car? Yes, go ahead.
X minus 20.
What does x represent again?
The speed of the car.
Mm-hmm. So what's the speed of the car?
X.
X.
Oh.
So x is going to be the speed of the car. Now we need to figure out the time on the train. Well, we need the distance divided by the speed. What's the distance that the train traveled? They don't give us that, but we should be able to figure that out based on what they did give us. Yeah, Jake?
90.
90. Total trip is 120, and she did 30 by car. So the distance of the train is 90. And what's the speed of the train? Or how are we going to represent it? We don't have an exact number. Yep.
X plus 20.
It's x plus 20. And there's your equation that represents the time it would take to do the trip. You tell me how fast the car was going, I'll fill it in for x, and I can calculate the time. Okay. Any questions on that equation? All right, so now we're going to take a look and just kind of analyze that a little bit. by finding asymptotes, roots, EBM, and then we'll do a sketch. For some of the things they want us to find, it's going to be easier if we had one fraction. I have two separate fractions. If I want to add those fractions together, what do I have to make sure that I have? Yep.
Common denominator.
Common denominator. The easiest way to get a common denominator is just multiply the two that you already have together and then figure out what's missing in each fraction. So the common denominator would be x plus 20. What is the fraction on the left missing in its denominator to make it the common denominator? Yep.
Plus 20.
Well, it's missing, so it's got this, right?
Oh, x plus 20.
It's missing the entire x plus 20. So what would we multiply top and bottom by? X plus 20. So x plus 20, x plus 20. Now, what is the denominator on the right missing to make it have the common denominator? It's missing the x. So we're going to have to multiply top and bottom, because whatever you do at the top, you've got to do at the bottom when you're trying to find a common denominator. And now the denominator on the left is x plus 20. The denominator on the right is x plus 20. Leave it like that. Don't FOIL it out or distribute it out. Now in the top, we have to do that out. That's going to be, I'm just going to do it off to the side, and then I'll put it up here. Actually, let me do it right here. That's 30x plus, Matt, what's 30 times 20?
600.
600. So that's on the left, and then on the right, there's only one term to multiply, so it's not a distributive. What's, Abigail, what's 90 times x? 90x. So Jack, what do I end up with in the top when I combine like terms?
120x plus 600.
Yeah. So again, I just combine them because when we want to find certain things, it's easier to have it combined. Yeah, and that's also easier for me to type in on the calculator. It's less fractions. All right, let's do the EBM first. Remember, EBM is the highest degree term in the top divided by the highest degree term in the bottom. How about Ethan, what's the highest degree term in the top?
120x.
Yep, 120x. And now you have to be a little careful with this one. What is, or I'll say it this way, what would be the highest degree term in the bottom? Yeah?
X squared.
It would be x squared if you did it out. Okay? It would be x squared. And when I reduce that as much as I can, what am I left with? When I cancel out, what will cancel here? Yeah.
120 over x.
We're going to be left with 120 over x. That is your EBM. Remember, E stands for end. End is very far away. Okay? It predicts, it's a model for the behavior at the end of the function. Well, the end of the function is values very far away, to the left or to the right. So that should give you a hint. You use the EBM to find your horizontal asymptote. And does anybody remember what you let x approach to find a horizontal asymptote? Remember, this is at the end of the function. So think about what value is x as you get towards the end. It's approaching what? Yep.
Infinity.
Infinity. So if you let x approach infinity here, the denominator in the EBM gets huge and the numerator stays the same. What does a fraction approach if the denominator is getting infinitely big? Yeah?
0.
It approaches 0. And remember, horizontal asymptote is always y equals. Let's do vertical asymptote. somebody remind me, how does the equation of a vertical asymptote always start? Yep,
X equals.
that's always x equals. And if you remember it from vertical asymptotes, that is the zeros of the denominator. How many vertical asymptotes am I going to have in this problem? Yeah.
2.
I am going to have 2. You have as many vertical asymptotes as you have factors, assuming they're distinct. And these are 2 distinct factors. First factor, second factor. Francesca, what would make my first factor 0?
Minus X.
We need a number that we could plug in. Well, let's start with the second one. What would make my second factor 0?
Minus X.
But it's got to be a number. You have to have a number you could plug in here so that when you do it, it causes me to divide by 0.
Minus 20.
Minus 20. Okay, so that's one of my vertical asymptotes. And what would make this first factor come out to 0? You really just set that factor equal to 0 and then solve. Don't think about it too hard here. It's not. It's easier than the other one you just did. Yeah.
0.
0. What would you plug in here to make that factor 0? You would plug in 0. What would you plug in here to make that factor 0? Negative 20. So we have 2 vertical asymptotes. I'm not saying that they make sense, because x is the speed of the car. So what does negative 20 really mean? Nothing in terms of the word problem, but they asked us to find it. So we've got asymptotes, the EBM, and the last thing we need are the zeros, or the roots. Same thing as asking for the x-intercepts. All right, so remember, the roots, like if I just give you like a simple equation just to look at for a second, the root is the number you can plug in for x, so you get 0 for y. In this case, the root is negative 2. 2 times negative 2 is negative 4, plus 4 gives me 0. So the roots are when you set your equation equal to 0 and solve. So now, let's pretend that we did that here. We would have a fraction equal to 0. What's the only way that a fraction can ever come out to 0? Yeah.
If the top is 0.
If the top is 0. That's the only way that it can ever come out to 0. So in order to figure out what you would plug in for x to make this come out to 0, set the top equal to 0 and solve. So that's going to give me 0 equals 120x plus 600. We could just minus the 600 to the other side. And Zach, what would be my last step to get x by itself? Divide by 120. That's gone. That's gone. And what do I get for a x value for the root? Yeah?
Negative 5.
-5. So in other words, if you plug in -5 for x, you will get 0 for y. And that's the definition of a root. And that's everything they wanted. So a little bit of a review. We've done all that before. But it was 2 weeks ago, so I just wanted to kind of refresh that. Questions on how I found any of those? Okay. So now, using that same problem, it says that Sarah has 2 hours to complete her trip. I want to know what speed the car has to travel at to complete this trip in 2 hours. So let's write down the formula again. T of x equals, I'm going to write down the version when we combined it, 120x plus 600 divided by, was it xx plus 20?
Yeah.
Okay, thank you. So we have to do something with this. Anyone have a guess what we would do with that 2?
Did you set it equal to 2?
Yeah, you're going to replace the t of x with 2. You wouldn't plug it in for x. Remember, x is the speed of the car. That's what I don't know. I'm not saying the speed of the car is 2. I'm saying the time to do the trip is 2. So we would take this 2 and we would fill it in that box. 2 equals 120x plus 600 over xx plus 20. Let's do this algebraically first. What could I multiply both sides by so I don't have a fraction anymore? Just looking for something I could multiply both sides by so it gets rid of my fraction. Sarah?
X squared plus 1x.
Yeah, in fact, I can just, for now, I'm going to have to do what you just said in a minute, but I'm just going to leave it as xx plus 20. And if I multiply that on the right, that cancels out. And I'm going to multiply by x plus 20 on the left. Now I have a distributive property. I'm distributing a 2 and an x to what's inside the parentheses. So Matt, what's 2x times x?
2x.
Not just 2 times x, but 2x times x.
Squared.
Yeah, squared. And what's going to be my next term when I distribute what's left? Yeah, Jake?
Would be x and then x plus 20.
So when you distribute both of those, what do you get?
Oh, you get 40x.
40x. If you want to stick that 2 in front, think of it like that, that's fine. It's 2x times x and 2x times 20 equals 120x plus 600. Now, Abigail, what kind of equation is that? It's the kind of equation we've solved before.
I forget the name of it, but both sides equal to.
So when both sides are the same, that's an identity. I don't think this is going to come out to an identity because I have squared terms on the left and I don't have the squared terms on the right. So we don't have the same thing on the left and the right. But does anyone else have an idea, Jack?
Be a quadratic.
It's a quadratic. And whenever we want to solve a quadratic, what do we always get it equal to?
0.
Yeah. So let's get it equal to 0. I'm going to put everything on the left, and then we'll go from there. So 2x squared. Let's minus the 120x. 40 minus 120 gives me how much? Careful.
Negative.
Negative 80. So So we got that, we got the x's, and we would minus the 600. Not necessary, but there is something I can do here to make all these numbers a little smaller. Yep.
Divide by 2.
You can divide everything by 2. Now, I don't think that that's going to be factorable. In fact, I know it's not. So how are we going to have to solve it if we can't factor it? But this isn't bad because we have a method for always solving equations when the highest exponent is a 2. Yep.
Quadratic formula.
Quadratic formula. So negative b plus or minus the square root of negative 40 squared minus 4ac all over 2a. Now, under the root, I have 1600 minus a negative number. So, Francesca, what's going to happen there?
That times 4 times negative 300.
And because I'm going to end up subtracting a negative number, what will happen?
A positive.
Yeah, this is all going to end up being added because it would have been minus a minus. So now, Matt, what do I get under the root?
Let's see. $2,800.
Good. So we get 2,800. And now we're at the point we're just going to type that in and see what we get. And this will tell us the speed of the car if she can complete the trip in two hours. Now, something a little weird here, plus and a minus. Does that mean we're going to get two different answers? Meaning she could drive at this speed and somehow do it in 2 hours, or magically drive at some other speed and also get the trip done in 2 hours? What do you think is going to end up happening here? Yeah?
One will be a negative, one will be a positive.
Yeah, one of the answers is going to be a negative, which won't make sense in the context of the word problem. Let's do the positive, because we know that's the one that makes sense. So 40 plus the square root of 2,800, divide by 2, and we get a speed of 46.46. And if you look back at the original problem, I think it said 2 hours, and the distances were in miles. So we know this is miles per hour. Okay. Now, if you did 40 minus the square root of 2,800, you're going to get a negative. That does not make sense in the word problem. Okay, so you always want to be careful about including negatives. Now, let's kind of think about the same thing, but graphically. So we had 2 equals, I forgot what it was, 120x plus 600 over, what does that come out to? X squared plus 20x. How could I solve that on the graphing calculator? Yep.
If you plug in 120x plus 600 in the parentheses,
All right.
divided
120x plus 600, yep, in parentheses.
and then divided by x squared plus 20x in parentheses.
X squared plus 20x. All right.
For your y2, set it equal to 2.
Yeah, and the y2 set it equal to 2. Now let's think about our window a little bit. The slowest speed of the car could be what? Car can't go slower than this. Yeah, can't go slower than 0. We already know the speed is going to be 46.46, but if we didn't know that, I might say, well, let's go up to like 65 and see if that's high enough. Y is the time. Well, what's the shortest amount of time we could do this trip in? Or what would be the shortest amount of time we could approach, but we could never reach? Yeah? 0. You can't instantly travel. That's impossible. Even the fastest thing we know of, the speed of light, has a time it takes to go from point A to point B. We can't, at least we don't think we can go faster than that. So no matter how fast you go, it's still going to take some amount of time to get from here to there. So 0, what would be the maximum amount of time? Well, there really is no maximum. I mean, if you drove 0.0001 miles an hour, it would take a very long time. So let's just set our maximum at 10 hours and see what it looks like. So you can see the faster you go, the less time it starts to take. The slower that you go, the more time the trip starts to take. We're going to see where it doesn't take 2 hours. So what do I have to calculate? Yeah.
The intercept.
The intercept. And we're hoping it's 46.46. So second calc, intersect, pick a point on the blue, point on the red, and then move your guess somewhat close. It doesn't matter too much because there's only one point where they cross. But if you look at this, we get exactly the same thing that we got using the quadratic formula. Okay, so 46.46 miles per hour. All right, so any questions on that, especially the algebraic way? Okay, now everything we did here was fine, but we have to be a little bit careful because we multiplied both sides of this equation by something with a variable. If you do that, you have to check your answer. Because when you multiply both sides by something with a variable, you can end up making an extra answer to the equation that shouldn't be there. That's called an extraneous solution. It's a solution that you created because of a step you took in the problem, and that solution shouldn't be there. Now, the calculator will never give you an extraneous solution, which is exactly why I might ask for it on the test. Because there is no way to figure out an extraneous solution using a calculator. You have to do the algebra, look at what you got, and say, okay, that's extraneous. I'm going to tell you how you can know that. So an extraneous solution is a solution to the new equation you made because you multiplied both sides by something with a variable, but it is not a solution to the original problem. So how do you see if something is an extraneous solution? You need to check it. And usually what happens if it's extraneous in this kind of problem is when you try to check it, it causes you to divide by 0, which you can't do. As an example of an extraneous solution, let me show you a very simple equation. X minus 1 equals 0. What's the answer to that problem? Ted?
-1.
So if you plug it in, does -1 minus 1 give you 0? Yeah. 1. 1 minus 1 equals 0. Does everybody agree that 1 is the answer? Is there anything else there that you could plug in for x and it would work? Well, Kate, what do you think? No, there is nothing else. That is the only answer. Now, let me multiply both sides of that equation by a variable and watch what happens. If I multiply both sides by x, I get that. X squared minus x equals 0. Let's see if 1 still works. Then what's 1 squared?
1,
Minus 1?
0.
0. So my original answer still works. X equals 1. But there's another answer that works here. What else could you plug in for x? And it would come out to 0. Besides 1. Yeah?
0.
0. 0 squared minus 0 is 0. So that is a solution to this new equation. Does 0 work back in the original equation?
No.
No. So by multiplying both sides by x, you created an extra answer to the problem that does not work in the original equation. And the extra answer here is 0. All right. So let's look at this one. And this is the strategy we're going to use. We are going to try to multiply by something that would cancel out all of our fractions. Let me show you an example that's much simpler, and then we'll apply it to this one, which is a little more complicated. Let's say we had 1/3 plus 1/4 equals 5/6 x. Okay, that's kind of a mess of an equation to solve because I have all these fractions. But there is something I could multiply all 3 of these by. It has to be the same thing everywhere. And all the denominators would cancel out. Anybody see what number I could multiply everything by? Trying to find the least common denominator of all the denominators I have. 3, 4, and 6. So it would be a number that they all divide into. Evenly. Jack? 12. So watch what happens if we multiply everything by 12. Times 12, times 12, times 12. 3 goes into itself once, 3 goes into 12 4 times. 4 goes into itself once, 4 goes into 12 3 times. 6 goes into itself once, goes into 12 2 times. Now the equation that you started with in red is now 4 times 1, and then 1 times 3 equals 5x times 2. Okay, I don't know about you, but that seems a lot easier to solve to me. I can quickly see the answer is 7/10 without even having to really do anything else. Just 7 divided by 10. But when we had all these fractions in here, it made it more complicated. Right? I couldn't do that as easy. So we multiplied everything by something that canceled out all these denominators. Right? So now let's try that same idea on this one. So I have 2x divided by x minus 1 plus 1 divided by x minus 3 equals 2 divided by x squared minus 4x plus 3. And I'm going to give you a hint on the right-hand side. Try doing that and watch what happens. Does anybody see how the quadratic on the right-hand side would factor? Yeah.
It would be x minus 3 and x minus 1.
Yeah, it would factor into the same 2 denominators that are already on the other side. Well, that makes it a lot easier. If that didn't happen, then it would be much harder. So now, does anybody see what I can multiply this, and that by? And it will cancel out my denominators everywhere. Well, what would you want to multiply the first fraction by to cancel out that denominator? Just the first one, yeah?
Would be x plus 1.
If you multiply by something that's not in the bottom, then it won't cancel it out. So like, if you want to cancel something out, you have to have the same thing in the top and the bottom of a fraction. So what could we multiply that first fraction by to cancel out the denominator? Anyone have a guess? Yeah?
X minus 1.
Yes, you multiply it by x minus 1. Now, if you do it there, where else do you have to do it? Yeah?
Everywhere else.
Everywhere. So that's fine. Let's multiply by x minus 1, x minus 1, x minus 1. But if you do that, it's only going to cancel out the denominator of the first fraction. What would you have to multiply to cancel out the denominator of the second fraction? Yeah?
X minus 3.
And that's fine, but you have to do it everywhere. You can't just do it to the middle. So let's do it here, here, and here. Now, what about the third denominator? What's going to happen there? Yeah?
You're already basically multiplying it by what it is.
I'm already multiplying everything by what that denominator is, so that denominator is already going to cancel out because the two factors that make it up were already used in the other two denominators. If they were not used in the other two, then this problem gets very hard. Okay? But they were. So now let's cancel out what we can. The x minus 1 and the x minus 1 is gone. The x minus 3 and the x minus 3 is gone. What about on the right-hand side? About Sarah, what's going to be gone on the right?
The x squared minus 4x plus 3.
Right, because that's what you're really multiplying everything by. If you FOILed it out, it's x squared minus 4x plus 3. So this cancels all of that. Now, everything that's left is a distributive property. This times that. Now, this is the tricky part, because if this was a negative, it would really mess some people up. It's this times that. Now, you might say, well, in this case, you're just distributing a plus 1. You're right, it's just a plus 1, so that doesn't really matter. But if it was a minus, or that number wasn't a 1, you're always distributing this symbol and that number to whatever you have left in the parentheses. All right, and just to get the right side done with, what's, Francesco, what's left on the right side?
The x
Minus 1 and x minus 3.
No, those canceled out.
And 2.
Just the 2. So remember, the x minus 1, x minus 3, that is now gone because that denominator is what we multiplied everything by. How about Matt? What am I going to get when I multiply the 2x times the x minus 3?
2x squared minus 6x.
All right, so there's my first one. Now we're going to distribute the plus 1 to the x minus 1. So Abigail, what does that give me?
x minus 1.
Just x minus 1. And I'm just going to move that a little closer. And Jack, what kind of equation is that?
Quadratic.
Quadratic, easy, just get it equal to 0. And if you can factor it, that's easier. If you can't, use quadratic formula. So 2x squared minus 5x. Just bring the 2 over to the other side, and now we have minus 3. Casey, what would be my first term in each set of parentheses if I want to factor that? Yep, an x and a 2x. And Ethan, what about my signs? Positives, negatives, or one of each?
One of each.
Yep, we're gonna need one of each. I would try it like that. And Zach, 2 numbers that multiply to give me 3. Zach. Thanks. 2 numbers that multiply to give me 3.
1 and 3.
1 and 3. And if you just guessed, then you guessed the right order. So 2x squared, 2x times negative 3 is negative 6. Negative 6 plus 1, negative 5. Perfect. Now, Tyler, what do I do with each of those factors?
Make them all equal to 0.
Yep, make each one of them equal to 0. So I get negative a half. And Ashley, what about my second factor?
X equals 3.
X equals 3. Now, at any point in this problem, did I multiply both sides of the equation by something with a letter? Yes, I did. So that means I need to check and make sure these answers work. Negative 1/2 and 3. Let's scroll back up. Any thoughts about trying to plug in negative 1/2 or 3 for x?
Wouldn't 3 not work? Because it would make you divide by 0 in this and 1 on the second one.
Yeah, in the second fraction, the denominator is x minus 3. If you try to fill in 3 for x, you're going to have 3 minus 3. You can't do that. So that means 3 is an extraneous solution. You can check the other one, the negative 1/2, but it does work. Okay. So this one works. This one is extraneous. Again, there's no way for the calculator to graph and give you the extraneous answer or anything like that. You have to find it either using factoring or quadratic formula. All right, any questions on that one? So that's a pretty typical kind of rational equation where this denominator is the product of the other two. Again, if it wasn't, it would be a lot worse, but it will be. Let's try this one and then, yeah, all right, let's try this one. First, before we even start doing anything, does anybody see how the denominator on the right would factor? Yeah, Matt?
X plus 2.
Yep, that's part of it. What else?
And in parentheses, you have x on the outside.
Good, nice job. X plus 2. So it's going to factor into the two denominators we already have, which I told you would always happen. So, now, can anybody tell me what we would multiply all 3 of those by to eliminate all my denominators? Yep.
X plus 2.
X plus 2. So x plus 2, x plus 2, x plus 2. In the first parenthesis, the x is gone. In the second set of parentheses, the x plus 2 is gone. What about in the third, in the fraction on the right-hand side? What's gone there? Oh, the whole thing. Right? So what's left on the right-hand side now? Francesca? Yeah, I'd just like to get that one out of the way, because that one's easy. Now this is a distributive property. X minus 3 times x plus 2. So that's x squared plus 2x minus 3x. What's plus 2 minus 3? What does that give me? Yep, that gives me a negative 1x, and negative 3 times positive 2 is negative 6. So that's what you get when you do x minus 3 times x plus 2. Now, again, being careful, what are you distributing to the x in that second fraction? Yeah? The positive and the 3. Again, you might say, well, what's the point of the positive? Well, if it was a negative, it needs to go with it. So positive 3 times x. And then that equals negative 6. All right, let's combine like terms on the left. Anybody notice what's going to happen to that negative 6? Yeah?
It's gonna get canceled out.
It's just going to cancel out because if you add 6 on both sides, it's gone. That's going to make our next step very easy. So all we have is x squared plus 2x. I'm just going to move the equals 0 closer. Now, let's factor that. And just like we did before, tell me what two numbers would make that equal to 0. Ashley?
X equals 0, x equals
X equals 0 and x equals negative 2. Did we multiply both sides by a letter at any point? Yes, we did. Let's go back up and check 0 and negative 2. Any thoughts about plugging those numbers in? Yeah?
Negative 2 won't work.
Negative 2 doesn't work because if you filled it in right here, that was a plus sign. You cannot put negative 2 in right there. Yep?
0 won't work either.
0 won't work either. Because if you try to fill in 0 here, you'd be dividing by 0. So what that means this problem has no solution. So there's 3 things that can happen. You can get both answers don't work. One answer works, the other one doesn't. Or they both work. Those are the 3 things that can happen. So you've seen when they don't work, and you've seen when one of them works and one of them doesn't. You just have to check them, that's all. All right. Questions on it? All right. So now, the last thing we're going to look at is leading us into problems that have that in them. When a problem has a less than or a greater than, it's not an equation anymore. Does anybody remember what we call it when your problem has a less than? Yeah?
Inequality.
An inequality, and that's what this problem is. The answer here is not going to be the speed of the car equals a number. It's going to be an inequality because it says at what possible rate could Sue travel to make sure she completes the trip in less than 2.5 hours. Not exactly 2.5 hours, just less than 2.5. So kind of like we did before, I already have the equation in the calculator still, I hope. I got the right-hand side already typed in as a combined fraction. Where's this 2.5 going to get plugged in? Yeah.
Left to the equal sign.
Left to the equal sign. You're going to replace t of x with 2.5. We already replaced it with 2, so let's just change the 2 to 2.5. Alright, so let's hit graph. Again, there's the speed of the car. It's the same problem we already did. There's where it hits 2.5. Okay, what do I need to calculate? Yep, I'm going to calculate the intercept. And now we just have to be careful about how we write the answer. Second calc, option 5. Hit enter. And it says they intersect when x is 34.89. So what speed would Sue have to travel at to make sure she completes the trip in less than 2.5 hours? Yeah.
At least 34.88.
At least 34.88 miles an hour. What does that mean in terms of an inequality if you say at least that much? Her speed has to be, yep, greater than or equal to. Now we just have to see, are we supposed to include the equal to? It does say strictly less than 2.5 hours, so she has to go greater than 34.89. If it says, what speed could she travel at to complete the trip in 2.5 hours or less, then we could have put the equal to. But this strictly said less than 2.5 hours. And that's it. Any question on how we solve that inequality? Now, what can happen when you're solving an inequality algebraically that doesn't come up with an equation? If you multiply both sides by something, you're supposed to do something. Yep.
If you multiply both sides by a negative, you're supposed to flip the sign.
Right. If you multiply or divide both sides of something by a negative number, you're supposed to flip the sign. So let's say this problem was this problem. You can't use the same approach to solve it. Because if you look at it and you say, okay, well, I'll multiply both sides by xx plus 2. My first question would be, okay, is xx plus 2 positive or negative? Because if it's positive, you're supposed to keep this sign the same way. If it's negative, you're supposed to flip that sign. Well, you don't know. Xx plus 2 is a variable. I can't tell you if that's positive or negative. So because we wouldn't know if you're multiplying by a positive or negative, you can't solve using this method. So I'll finish up by showing you what we do. Two ways you can solve it. If it's a really complicated problem, you're going to have to solve it graphically, just like we did the last time. You have to put something in y1, something in y2, calculate an intersect, and then look and say, okay, is my answer everything more than the intersect, or is it supposed to be everything less than the intersect? It depends on the problem. If it's a simple enough problem, I might ask you to do it with a sign chart. Okay, a sign chart only works for a problem that is factorable. If you have a problem that's not factorable, you're going to have to do it graphically. Okay, and I'm just going to make up a problem to take a look at. Okay, let's try this. So let's try solving x squared minus 2x minus 3 is less than 0. So again, the sign chart is only going to work if you can factor it. And if I ask you to solve with algebra, then it will be factorable. All right, so how does x squared minus 2x plus 3 factor? Yeah.
X minus 3, x plus 1.
So we would have an x minus 3 and an x plus 1. And now to make a sign chart, that's where you make a number line, and you look at where it's positive and where it's negative. Let's start with the first factor. What would you plug in for x to make that first factor 0? Yep, 3. What if you plugged in a number smaller than 3 right there? What kind of answer would you get? Yep, you get a negative. If you plugged in a number bigger than 3, like 5, you get a positive. Let's do the same thing for x plus 1. What would you plug in for x in the bottom one to make that 0? Yep.
Negative 1.
-1. And if you plug in a number smaller than -1?
Negative number.
Negative? What if you pick a number bigger than -1, like 0? Yeah,
Positive.
that would result in a positive. So now we have two roots, -1 and 3. Let's look at the number line. Those two roots are going to split your number line into 3 sections. The less than -1, the between -1 and 3, and the more than 3 section. We're looking for the sections that come out negative. Okay, let's see if we can find those sections. Let's start with the less than -1. Tyler, if I plug in a number that is smaller than -1, what section would I be in my top number line?
Negative.
Smaller than -1 would be somewhere like down in that area. What if I plug in a number smaller than -1 in my bottom number line?
Also be negative.
It would also be negative. And what do you get if you take something that's a negative times something else that's a negative?
Be positive.
You get a positive. Let's check between -1 and 3. Ethan, if I was between -1 and 3 in my top number line, where would I be?
Be negative.
I'd be somewhere in here, like that's the negatives. What about between -1 and 3 in the bottom number line?
Positive.
That would be somewhere in here. That would be in the positive. What's a negative times a positive?
A negative.
That's a negative. And does anyone remember what's supposed to happen with these sections? We don't have to really check the last one if we know the pattern. Yep,
Doesn't it alternate?
it's supposed to alternate positive, negative, positive, or negative, positive, negative. Now you have your answer, you just have to look and see which sections do they want. They want the less than 0 section. Well, the less than 0 section is from there to there. That's the negative section. That's from -1 to 3. Not including -1, not including 3. If they had given me that, and they put an equal to, what would these parentheses change to? Yep, they'd be brackets instead. Yep, they would be brackets. So this is an open interval because we are strictly less than 0, not less than or equal. Right? And that's how you can solve a relatively simple inequality as long as it's factorable. Now, if you had something like that, that is not going to be factorable at all. Okay, so let me finish up just by doing this one the way we did the car problem. I'll put what's on the left in y1. Okay, other than being a lot to type in, it's not really that bad. Minus 3x cubed plus 2x, oops, didn't mean that. 3x cubed plus 2x squared. Okay, If you forget something, you can always just insert. You don't have to type the whole thing all over. Plus 2, and then divided by x minus 2. Are the parentheses important around the numerator and denominator? If you actually had a numerator and denominator? Like that? Yeah, they are important. And then we're looking for where that graph is above 15. Now, what's happening when x equals 2? In that one, we talked about this at the beginning. When x equals 2, you're going to get a what?
Whole.
Not unless there's a common factor in the top and the bottom, which I don't think there is.
Asymptote.
So you're going to get an asymptote at x equals 2. So let's set our window. 65 is probably more than we need. Let's go like 25. Let's go negative 20. And let's try negative 20. I'm just trying a window. I don't really know. But I know I need to set my y max at least 15. So let's try 25. All right, so it looks like this graph is in 2 pieces. And I'm looking for where it's above 15. All right, looks like that's going to happen in 2 spots. It's going to happen in that spot, and then it's going to happen again in that spot. Well, I know I don't want to go any lower than 2, because if I go lower than 2, all of a sudden I jump down here. This is the other side of the vertical asymptote at 2. So you don't want to go past that dotted line, which is a vertical asymptote at 2. You go past it, now you're below 15. You're below the red line. So don't go past the dotted line, but you can go right up to, and I would have to zoom in and find that intercept. See if I can find it relatively quick. I'm looking for the one on the left. So from 2 up to, second calc, intersect. And as long as you're closer to the left, should give me the one on the left. Give me the one on the right. Okay, let's try it again. Just make sure your cursor, my cursor must have been on the wrong spot. Up to 2.22. So I can pick any point between 2 and 2.22, and it'll put me on that section. Or, I wish I had written down the other one, I already did it. I forgot what it was. I think it was 2.67 maybe? Yeah, 2.68. Anything from 2.68 to infinity. That section's just going to keep going up forever. Those are the 2 sections where I'm above 15. Okay, don't worry about the bottom one at all. That's below. Okay, so solving on the calculator is just really using an intersect. All right, so those are the questions for tonight. Okay, 1 through 13 odd. And then 20, 22, 24, 28, and 31. And we'll take a look at that tomorrow.